This is Math 251, section 11.4. We've been talking about one way to multiply two vectors, namely the dot product or scalar product. And in this section, we're going to be looking at the vector product, also called the cross product. So we're still multiplying two vectors, but as you're going to see, this time we're going to get a vector answer. You may remember that the way we kind of went about figuring out what the dot product should look like was what made sense when we looked at work done in the sense of physics. We're going to start similarly this time and say, what if we're doing something but we're not actually pushing an object along a straight line? Instead, we're turning or twisting something. Imagine, for example, using a wrench to twist or turn a bolt. Has there been any work done in the sense of physics? And the answer is actually no. Remember, work is done when a force is exerted through a distance. When we push here, we're not moving that bolt at all in the direction of the force. It's going in or out of the board, but we're not moving the bolt in the direction of the force. So there's not been any work done in the sense of physics, and yet we know we're doing something. So we need a new concept to measure this twisting power, and we call this the torque. It's analogous to the concept of work, but for a twisting motion rather than a pushing or horizontal motion. So, when you use a wrench to turn a bolt, what affects the amount of twisting power you're going to get? Well, a number of different things. First of all, probably the most obvious, how much force you apply, right? The harder you push, the more twisting power you're going to get. So the amount of force. Secondly, anybody who's ever tried to loosen up a stubborn bolt knows that if it's not working, what do? Usually you try to get a longer wrench, right? So the length of the wrench is going to affect the amount of power you get to turn that bolt. Oops, wrench, I didn't spell that right. There we go. All right, thirdly, and perhaps the most subtle, the third thing that affects the amount of power you get is the angle at which you apply the force. This is something that most of us do kind of automatically. We usually use almost a 90-degree angle probably when we try to push against a wrench because that gives us the most power. If you can imagine coming in and directing your force, say, this way, maybe you'll still be able to turn it, but you certainly don't get as much leverage. You don't get to turn your bolt nearly as easily as you do if you use a nice 90-degree angle. So the angle at which the force is applied also affects the amount of power you're going to get. And we get the most at that 90-degree angle. All right, let's start putting some of this information into the diagram. We've already got our force vector kind of diagrammed for us right here. So let's just assume that's our force F. The amount of the force then could be the magnitude of F. For the length of the wrench, I'm going to go ahead and put in a wrench vector, starting from the bolt, going out to the end of my wrench. And I'm going to call that R. So the length of the wrench vector would be the magnitude of R. Lastly, the angle at which the force is applied. So that would be the angle theta here. And I'm just going to mention that right now these two vectors are not together in standard position. If I assume that my origin is here at the bolt, you'd have to imagine taking this wrench vector, or excuse me, this force vector, and translating it over here to the origin. That would give us the same angle theta in standard position. So the angle, which we'll call theta, in between the force vector and the wrench vector. So from this, we're going to define the magnitude of our torque. How much twisting power are we getting out of this? And it will make sense, hopefully, that we're going to want to incorporate all three of these items. So let's just go ahead and put in as multipliers the magnitude of F times the magnitude of R. Both of those contribute to how much torque or twisting power we get. And then typically we don't just put in theta, right? Usually it's a trig function of theta. With the dot product, it was cosine. But let's think about what would make sense here. We get the most force at a 90-degree angle. Which of our trig functions is largest at 90 degrees? Sine or cosine? Well, sine of 90 degrees is 1, as large as it can get. So this time, to incorporate theta, we're going to go with a sine theta. Maxes out at 90 degrees. So that's the magnitude of our torque. Now, is torque truly a scalar? Right now, this is a scalar quantity, right? 2 magnitudes times a sine function, definitely scalars. But does this twisting power actually result in a true scalar quantity, or does it act in a specific direction? You all know that when you turn a bolt, it does move. It just doesn't move in the direction of the force. It actually moves perpendicular to the wrench and the force, right? It either goes into the board or out of the board. So it actually does, this bolt does move specifically in a direction perpendicular to the wrench R and the force F. If you think about this for just a moment, we can actually define this direction rather well, and I think it's going to remind you of something that you already know. If I've got this bolt here, so there's my origin, that's the bolt. I've got a wrench vector R, and I'm applying some force F here at the end of it. Then if I take that F and sort of translate it back to the origin, that gives me my angle theta. Which way is this bolt going to move? Well, let's see. If this is my wrench and I'm pushing this way, it turns my wrench to the left. And you remember the old saying, righty-tighty, lefty-loosey? We should be loosening that bolt, right? It should be coming up out of the page. This actually follows the right-hand rule that we discussed earlier in the chapter. If I take my hand, I'm going to put the heel of my hand at the origin and lay my hand along the R vector, curl my fingers toward the F vector in standard position. Notice my thumb comes up out of the page. That bolt is going to move upward. Now what if I turn this around? Here's R again, and this time I'm going to push this way for my F. So I'm pushing my wrench toward the right. That should tighten the bolt. It should go into the page, right? Again, you have to imagine F translated over here to the origin so that both are in standard position to see your theta. Now for my right-hand rule, again I'm going to put the heel of my hand at the origin, lay my hand along R, and I want to curl my fingers toward F. So in order to do that, I'm going to have to twist my hand this way this time. There, my hands along R, fingers curl toward F. Notice my thumb is going down into the page this time. So the bolt goes down into the page. So as far as the direction here, the direction follows the right-hand rule, is what we're seeing. So the bolt moves in a direction perpendicular to R and F according to the right-hand rule. All right, we're going to put all of these pieces together, and we're going to say this is a way to define vector multiplication as what we're going to call a cross product. The cross product of two vectors will have its magnitude defined this way, and its direction defined by the right-hand rule. We're going to put those pieces together on the next page. So here we go. The definition of the cross product of two vectors could be R and F, but I'm going to do it generically now as just W and V. W and V are then two vectors where theta is the angle between them. Then the cross product, W cross V, is defined as a vector. And this vector has two properties. Its magnitude is the magnitude of the first times the magnitude of the second times the sine of the angle between them, just like we were seeing on the other page. The direction, perpendicular to both W and V, based on that right-hand rule. A few things to notice. The cross product of two vectors then is a vector, has a direction as well as a magnitude. The cross product requires three dimensions. The direction of the cross product is perpendicular to both W and V, and the only way to get that to happen is to use the third dimension. And finally, cross product is not commutative. In fact, W cross V is equal to minus V cross W. Think about that bolt again to verify that in your head, right? When I did one direction, I came up out of the page. When I did it the other direction, I went down into the page. It reversed direction. All right, using this definition, it's relatively difficult to calculate the cross product unless the angle is given. And even then, it's really only the magnitude that we can easily determine. So far, we don't have a good way of defining a direction perpendicular to two known vectors. So we're going to have to do a bit of work on that. In order to do that, we're going to start with some special cases that eventually are going to help us out. So first of all, can we find W cross V for these two vectors? In this case, I think we can, only because notice there's a very specific relationship between W and V. V is just exactly 5 times W. And we know that when we've got one vector that's a scalar multiple of the other, they're in the same direction. V is just 5 times as long as W. Right? So same direction, V is just 5 times as long. What that means is we actually know theta in this case, right? The angle between those two vectors is 0, since they're in the same direction. So what that means is I can start to define at least the magnitude of my cross product. The magnitude of W cross V is going to be the magnitude of W times the magnitude of V times the sine of the angle between them, which is 0. But since the sine of 0 is equal to 0, that means that this whole product becomes 0. Well, if I've got a vector with magnitude 0, it has to be the 0 vector. Zero vector, or in 3 dimensions, we could just write it as 0, 0, 0. This is actually going to be true for any parallel vectors, right? If they're in the same direction, theta is 0, which zeroes out our magnitude. And actually, if they were in the opposite direction, theta would be 180 degrees. But the sine of 180 degrees is also 0. So the same thing would happen. On the next page, we have a little place where we can talk about the special cases of the cross product. Let's fill that in right now. It's actually at the bottom of the page. We'll come back up to the top. If W and V are parallel vectors, same or opposite directions, then W cross V is always going to give us the 0 vector because of that sine theta term being 0. We'll come back and talk about the perpendicular situation after we do example 2 at the top of this page. So in example 2, we're going to look at the specific cases of the coordinate unit vectors, the i's, j's, and k's. And I'm just going to go ahead and draw them over here. Let's see, I'm going to go in fourths. 1, 2, 3, 4. Let's call this 1. So I would look like this. Vector of unit 1, or unit length 1 on the x-axis. J is the vector of length 1 on the y-axis. And K will be the vector of length 1 on the z-axis. So there's I, J, and K. I would like to start out by calculating I cross J. Now, first of all, I know that the magnitude of I cross J is magnitude I, magnitude J, times the sine of the angle between them. But since I and J are on the x and y axes respectively, I know that's a 90-degree angle between them. I and J are unit vectors, so their magnitudes are both 1. So this is just 1 times 1, and the sine of 90 degrees is also 1. So the magnitude of I cross J is 1. Now what about the direction? Well, think about your right-hand rule here. You want to think about putting the heel of your hand at the origin, lay your hand along I, which is coming straight out of the paper, curl your fingers toward J, and where does your thumb point? Let's see if I can do that. It's not going to look like I'm putting my hand along I because I is coming out of the paper, so I'm just going to imagine putting my hand straight up, curling my fingers towards the y-axis, J. My thumb's going to point up. So the direction is up. Well, what's the name of a vector of length 1 that points straight up? Isn't that just K? So I cross J is K. We know that when we reverse the order of a cross product, we always get the opposite answer. So J cross I is going to be minus K. What about J cross K? Well, if you, again, put the heel of your hand at the origin, lay your hand along J, and curl your fingers towards K, my thumb's going to point straight out of the paper, and that's in the direction of the x-axis. A vector of length 1 in the direction of the x-axis is I. And the reverse will give me minus I. All right, finally, I cross K. My hand goes along the I vector, which is going to be straight out of the page, and I want to curl my fingers towards K. So my hand comes up straight out of the page, curl towards the positive x-axis, and I point to the left. To the left would actually be minus the J vector. So the opposite k cross I is the positive j vector. All right, so we know now what the cross products of all of the coordinate unit vectors are. Rather than having to get out your right-hand rule and try and figure it out every time, there's actually a fairly easy memory aid to help us with this. It looks like this. If I just kind of form a little circle with my vectors I, j, k in alphabetical order, when I go around the circle in the, what would that be, clockwise direction, my cross products are positive. Here's what I mean by that. I cross j is positive k. J cross k gives me positive I. K cross I gives me positive j. Right? And that corresponds with exactly what we had up here. Of course, if I were to go around in the other direction, counterclockwise, notice the I, j, and k are staying in the same position, just going around the other way. These would give me the negatives. I cross k is minus j. J cross I is minus k, and so on. So that can help. All right, so perpendicular vectors, not a whole ton to say. I will say this, that because for perpendicular vectors, we're always looking at a sine of 90 degrees, the magnitude will always just be the magnitudes of the two vectors multiplied together. The direction, there's not much we can do other than say use the right-hand rule. So the only thing I'm going to say about W and V being perpendicular vectors is I can conclude that the magnitude of W cross V is the magnitude of W times the magnitude of V. I've dropped the sine theta term because sine 90 degrees is just 1. All right, that gets us to the point where we can start to talk about how are we actually going to figure out how to calculate these cross products, because what we've got right now is not really useful unless we have a very, very special situation. We need a better method. We will look at that in our next video.